All right, so we're going to begin our Unit 2 test review. So the first thing we covered on Lesson 2.1 was different types of sequences and series. And specifically, we looked at two different types called arithmetic and geometric. Arithmetic, what does it mean if you have an arithmetic sequence? They're adding or subtracting to one another. Okay, they had a difference. A constant difference is what we called it. A common difference, actually. A common difference, which took the letter D. It had a common difference. The letter was D. And so what was our formula that we used to come up with at the beginning on Lesson 2.1?
A equals AK plus D and minus N.
Plus D, and then
Parentheses.
okay, and what I want to point out today, one more time, as somewhere along the way I reviewed you on this, but as I was thinking about how can we do find the common difference if we don't have terms that are next to each other quickly, it dawned on me, I should just do algebra here. So let me point out what I'm trying to say. If I wanted to get this common difference with the NK isolated, I'm going to isolate this part. How would I get rid of this AK?
Subtract or add it.
Okay, so this is the general, we'll call it the general form for arithmetic sequences. But if you wanted to solve for your common difference quickly, how you would do that is D times N minus K would be equal to, what'd you say to get rid of AK? You would subtract it. AN minus AK. And I'm going to show you some specific examples of this in a moment. Okay, so here is the general form here. But this would be if you solved it for the common difference, and especially if you had a sequence where they're not next to each other, meaning we're skipping values. Okay, so if it's not like A1, A2, A3, A4, so on and so forth. Okay, what about geometric? We did not call it a common difference. We use a different word.
Common ratio.
Common ratio, good. What's the difference between a difference and a ratio?
In the ratio, you're multiplying or dividing.
All right, great. And that used the letter R. So the formula here, we used the letter G. We said it was Gn equals GK. So the same start.
Parentheses R to the power of N minus K.
Yeah, I'm going to just do R like this, N minus K. And the reason I want to write it like this is because I think it'll be easier to remember because it's very comparable this way. The only difference is this is a plus, this is a times. Does it make a difference between A's and G's? No. Okay, and so once again, as I thought back and somewhere along the way, thought of, okay, what if we have terms that are skipping? What's the better way of finding our R? Well, it'd be to isolate this. So if we wanted to isolate this R to the power of N minus K, how would I get rid of this GK here? The opposite operation is not to subtract, it would be divide. So let's write underneath this that if you were solving for the common ratio, you could do this. R to the power of N minus K is equal to Gn divided by GK. And it would not matter if your terms were successive, or meaning the one after the other, or if there was a gap between them. So any questions over our formulas there? You need to know those by heart by the time you take your tests next class. Okay? So what I'm going to do now is I'm going to go, I think I came up with 3 different examples, maybe 4 actually, that we're going to use these formulas to solve the problem, okay? Good to change?
Good.
All right. So the first thing, what if we had to write an equation or rule for this sequence?
Looks like it's multiplying with that. Yeah.
It's multiplying?
Yeah.
So if it's multiplying, what type of sequence is it?
Geometric.
We call it geometric. And you're saying it's multiplying by 4. You're saying it's, and a way you can find that is, like I said, you could say R to the power of N minus K is equal to Gn divided by GK. That was the formula I just gave you. So let's just plug in. And how about this? Let's not even use terms that are back to back just to show you how the formula would work. Let's say this is, what would we call this term?
You do, there'll be GK.
G1, which is going to equal for the formula GK, good. Okay, what about 192? What would that be? G4, and G4 is going to represent GN in the formula. So I'm just going to show you, it would technically, it would be easier to take this and divide it by this one. What is 12 divided by 3? 4. That's probably what you did in your head, but I'm going to just show you how it works. So we could say R equals, well, what's the value of N? 4 is N.
4 minus 1.
4, and K is in the place of, or K is going to replace by 1, equals,
You do 192 divided by
there you go. Okay, so someone in your calculator, what is 192? Or we can do it this way.
64.
Oh, you already did it. Great. That's 64. And R to the 4 minus 1 is the same thing as
R to the power of 3.
R to the power of 3. Let's just do it this way. Okay, so what's the opposite operation of cubing?
Rooting.
You can root it to the third root, or you could raise it to the power of 1/3, whichever. It's the same thing mathematically. So I'm gonna cube root it. And by the way, it's an odd root, so you don't have to do plus or minus. Odds do not get a plus or minus. It's only the even roots that get a plus or minus. So what can multiply times itself 3 times and give you 64? We thought it was 4 earlier. Let's test it. What's 4 times 4?
60.
That's 16. 4 squared is 16. Times that by 4.
64.
It is 64. So R is 4. And so you see how that does work? Now, is that the equation though?
No.
So the equation would look like this. You would say Gn equals, now GK you do substitute. What is GK? 3 times our ratio of 4 to the power of
N minus 1.
N minus, and in this case, K is 1. Now, I don't really know if you remember this. So go ahead and box that up. That is an equation. But I think it was on, the title of the lesson was Manipulation of Exponential Functions. I believe it's lesson 2.4. We said we can do something with a power that's adding or subtracting. So I want to make sure you're aware of this, because this might not be the answer that shows up on the multiple choice test.
It's the rule of exponentials, right?
Yeah, it's one of the rules of exponentials. What can we do? Hang on a second, Javier, before you just yell at the answer. Let everybody think. What can we do if we have a power that's subtracting? What does that mean if you're subtracting a power of 1 there? An exponent subtracting is the same thing as the base dividing. Very good. So we could actually rewrite this like this. Gn equals. Morning. Okay. 3 times 4 to the n divided by 4 to the first. Y'all follow me so far there? A power subtracting is the same thing as the base dividing by that subtraction power. Now I'm going to change this 1 time for a final answer. Instead of saying this is 4 to the power of n divided by 4 to the first, I'm going to divide the 3 by 4 to the first. 4 to the first is what number? 4. So I'm just going to rewrite this as 3/4 times 4 to the power of n. Yeah, that could be your equation as well. And I'll put a Gn on the edge of that there. Now that is exactly the same. Those are one and the same answer mathematically. So what's my point in showing you this? If at first you come up with the equation and you don't see the answer and it's geometric, do not panic. Do not panic and think, what did I do? Simplify it to the form of the exponential functions. Exponentials are y equals a times b to the power of x. Simplify it into this form. You see how that's that form? What would replace a as far as this equation goes? Make sure y'all, because I wrote this backwards of this. Make sure y'all are following. What represents a? 3/4. That would be the initial value where it would hit the y-axis if you were plotting this. What would be the b? 4. The common ratio of 4 is the base. So it would be a 4. So that is in this form. Don't panic. All that to say is don't panic if you look and you're not seeing this answer. Just change it to more of the exponential form. A times b to the power of x. Just do your exponential rules. Okay? By the way, I'm going to give you more of those reviews in a second, specifically changing exponential functions. But right now I'm in the middle of arithmetic and geometric. So before I move on from arithmetic and geometric, I'm going to show you a couple more arithmetic and geometric equations. Am I good now? I will post this, so if you want to.
It's so when you do 4n divided by 4 to the power 1.
Yep.
Then it should be the same as 1.
Or
4 divided by 4 is still 4.
oh, you can't substitute simplify these two because they have powers.
Oh, okay.
So all you could do is subtract the power like that by 1, but you can't say 4 divided by 4. Oh, that's 1. So it's 1 to the power of n minus 1. It doesn't work that way. The math doesn't work out.
When you do the power, so you multiply the power of anything times that.
Yeah, let me show you why. This might help you. Let's get away from the n. Remember how we started here? Let's get away, just for example's sake. Let's say it was this. Here's why you can't say, oh, just cancel out the 4s. Because if you rewrote this as 4 cubed divided by 4 to the first, if you thought you could just simplify those 4s, here's why mathematically that's wrong. Is 4 cubed is the same thing as 4 times 4 times 4. And you're dividing that by 4 to the first, which is this one. You could simplify these two, but you could not simplify 3 4s with 1 4. Does that make sense?
It would be the same as
Which is 4 squared,
yeah.
or 16. Does
Okay.
that make sense now? So now we're back over here. That's why you can't simplify this by saying, oh, these cancel, these cancel. It's just 1 to the power of n. That's why you can't do that, is because that's saying there's an n amount of 4s, which we don't know. We don't know how many. There's just an n amount of them, however many n is over one of them. Yeah. Okay. I'm gonna leave that there.
Can you go back to this slide?
Oh, yep. One more time. All right. Moving on. What about this one? Determine the equation or rule for the following sequence characteristics. It's arithmetic. A3 is 25. A32 is 228. Okay, how could we come up with an equation for this?
So you plug in your 2 values into the other equation you gave us.
All right, so Javier is right. I'm gonna have someone else remind us. Katie, do you remember what the arithmetic formula is? Perfect. So in this problem, ASIF A3, what are we going to say A3 is represented by in the formula?
AK.
I agree. That's going to be our AK. Yeah, I'll do it this way. This is going to be our AK, which means K is going to be 3. In case you know anyone's not tracking with that, K is 3. AK is 25. K is 3. AK is going to be 25. K, though, will be 3, just to make sure we're clear on that. And what about A32? What's that going to be in our formula?
AK. I mean, AN, my bad.
AN. So AN, it's easier if that's your later term, AK your earlier term. That's our AN. So just to make sure everybody's clear, what is AN itself going to equal? 228. But whenever you see just an N by itself, what are you going to say that equals? 32. All right, great. So now let's plug in and we'll get an equation. Morning. So AN is
AN
228. AK is plus D 32 minus 3. Good. Let's simplify and solve for D. I guess according to PEMDAS, we need to do this subtraction first. That's 29. Can I rewrite that as, are you all okay if I write that as 29D?
Yeah.
You see how I just switched the order? 29D. 32 minus 3 is 29. And I put that in front of the D because that's how we usually do it. All right. What about now? What would I do to solve this problem? Subtract 225. And I heard Chris say that it's 204. Is that what he said? No, he said that's 203. Do y'all agree with that math? So 203 equals 29D. Divide by 29. What do we get here? It's 7.
Mhm.
Let's see, 140 plus 63. Yep. B is 7. All right, great. So does that mean if I just plug a 7 in right there, I'm done? What you do is you leave your A in. That does not change, but you replace AK with, what's our AK? 25 plus, what is our D? 7. N minus, and what's our K? 3. Okay. Now, just like the last problem, just like the problem we just did, you could box this up because this is the equation. That's it. That can find any, that's an equation or a rule that could find any term in that sequence. That would work. However, what if you come to the test and that's not there as one of the multiple choice answers? What should you do from here?
Simplify.
Simplify. If you remember, just like geometric's like exponential, and so you simplify to a times b to the power of x. Arithmetic is like what type of equation? Linear. So we need to get it into the form of y equals mx plus b. I'm not in there yet. So what could I do to simplify that?
You could do distributive property.
7n minus 21. Good. Can I simplify any further?
Yeah, you
Yes.
can combine like terms.
So it'll be
And 4 plus 7.
7
Or 7.
Yeah, so we're combining these two.
Yeah.
25 minus, and I'll do that after the 7n just to get it to y equals mx plus c form. So it's 7n plus 4. That would be a better answer. That would be what I would recommend. Would probably be your answer that you would see on the test right there. So now that you've seen it arithmetic, what I'm going to do here. So again, this is the equation. This could work as well. But this is more complex than the simplified version. Do y'all agree with that? This looks more simple. Now that you've seen it here, let's look back at what we just did. So remember how we had this equation? And then we solved it to here. This is the more simplified, the better version of it. Okay, so I just want to make sure you're aware of how to, but they both function the same way. Here I did an exponential rule to simplify. This time we did a distributive property to simplify. Questions over that? All right, I got at least one more. Maybe it's only one more. What about this one? Determine the equation or rule for the following sequence characteristics. I want to point this out. I use the letter A, but I don't mean that necessarily it's arithmetic. I want us to determine if it's arithmetic or geometric. What do y'all think? What type of sequence would this be? Okay. Serenity, why do you say geometric? What tells you it's not arithmetic? Okay, so
Maybe it has to do with this.
so if you check how much of it, if it's linear, it's going to be straight up rise over run, change of y's over change of x's. So how much are you changing from going from here to here?
Oh, you're subtracting 0.72.
0.72, and then how much is our x changing from? 2. So it'd be negative 0.72 divided by 2, which is negative 0.36. Now, is that the same slope going from here to here?
No. Well, no, not even.
No, because if this subtracted 0.72, you would need another 0.72 subtracted there. Is that a 0.72 subtraction? So what do we assume it is if it's not arithmetic? Not arithmetic. Because this is not equal to, let's go ahead just for the sake of the notes. How much do I change going from 0.892? Take 0.8192 and subtract 1.28 for me. I want to make sure I don't make a mistake here. .8192 minus 1.28. What do y'all get?
negative 0.4608.
46?
Yep, 4608.
4608. Okay, and then how much my x is changing by? From 2 to 4? 2. You divide that by 2, and this will be an easier calculation.
0.2304.
Are those equal to one another?
No.
No. So it's not arithmetic. There, we've proven it's not arithmetic. So what do we assume it is now? Geometric, and we should be able to change. Now, this time, do you remember the formula that I gave you to check for your ratio when I simplified it for the ratio? And again, what you could do is take this formula and isolate the r to the power of n minus k.
Equals Gn over Gk.
You could take this and just do the algebra. But what's the formula we're going to use here? It's going to be r to the power of n minus k equals Gn over Gk. Okay, so let's test it here. Let's test the first one using this formula. So r to the power of n's the later, k is the earlier. We're going to use these two first. So it'd be to the power of 2 minus 0. You see where I'm getting the 2 and the 0? Like the change of x, if you will, equals 1.28. Whoops, I did 1.8. 1.28 over 2. That would be r squared. How do you get rid of a square? Okay, so we should have a plus or minus, but because this is going to be C, I'm just going to leave it as a positive for now. Technically, well, no, I'll do my math right. I'll do a plus or minus here. I want you all to do type this in the calculator. You don't have to type in the plus or minus. And do the square root of 1.28 divided by 2. 0.8. Do plus or minus 0.8. Now let's test it again over here. One more time. We're going to say that this is r to the power of, between these two, what are my two powers going to be?
2 and 4.
It's the n and the k. So it'd be 4 and 2. So power 4 minus 2 equals 0.8192 divided by 1.28. I'm testing to see if the r's are equal to one another. That's what I'm doing right now. What is power of 4 minus 2? 2. So how do you get rid of a squared? That's r squared. You root it. So it'll be plus or minus the root of 0.8192 divided by 1.28. Type that in your calculator, see what you get. Again, don't type in the plus or minus, just type in the rest, see what you get. So the square root of 0.8192 divided by 1.28. I'm only seeing a few people using their calculators. I'd recommend you doing this. We're getting 0.8. All right, we can write an equation. Because these two are equal. Because these two are equal to each other. We found out an equation. So when you plug into the formula, it would be Gn would equal, what is GK? Which one are we going to use for GK? How about we use the first term, the 0, because there won't be anything to simplify. This will be simplified. That's the initial term. 2 times, what's our ratio, our common ratio? All right, I'm going to put that in parentheses. We don't know if it's positive or not negative, so I'll just do plus or minus 0.8 to the power of. If I say this is AK, by the way, then that means AK equals 2 and K equals 0. It's going to be n minus 0. What is n minus 0? N. That's already simplified because we had the initial term that made it easier. That would be our equation right there. One more time. The reason I have a plus or minus is because it's an even root. We added an even root. We don't know if it's the positive or the negative. If this said, right, an exponential model, then it is positive. Exponential itself, to be continuous, has to be positive. but geometrics, are geometrics continuous? Let me add that in on this next slide here. If you remember, the difference between exponential and geometric is this. All right, over here on the right. No, let me try that again. Sorry, pen. Here we go.
Into the graphs.
On the right, what type of graph did I just draw?
Geometric.
Not geometric.
Oh, exponential.
This is exponential. And what'd you call that? Growth or decay?
Growth.
Now, how do I know this is exponential and not geometric?
Because the line is not dotted. It's not a bunch of dots scattered around.
Line is continuous.
It's continuous. You can put in here, it's continuous. That's why. Continuous. What does it mean to be continuous? It means you could draw it without picking up your pencil. Continuous. There's no gaps or breaks in the graph. Chris, you stay with me?
Is
Okay.
this part of everything?
Okay. Yeah, you can just add this in on your notes there. Okay, now what am I doing? Am I drawing an exponential graph? No, what am I doing instead?
Added.
It's a different name. It's not exponential.
Geometric.
It's geometric. Now, how do I know this is a geometric
Because it's not.
sequence? Because it is discrete. The domain would start where your x, or usually we would do it with a variable n. So this would typically be y and x on exponential, but on sequences we might call it n and gn, or you could say that's y and you could say that's x, but typically we do it that way. And so here we would say n is greater than or equal to 0, and n are the whole numbers. So that's like that double W. Over here, you would say x is all reals. If that makes sense. So that's the difference in those two. One more time, what is arithmetic similar to?
Linear.
Linear, and the same difference between them. Linear is continuous. Arithmetic is discrete, and its n values greater than or equal to 0. All right. Moving on. We went into lesson 2.2 and 2.3. So 2.2 just showed how they were similar, as I just showed, and there's some differences. 2.3 was technically this lesson right here. This slide was 2.3. I did lesson 2.3 and 2.4 together, but 2.3 was this: understanding exponential growth versus decay. So I want you to think about, if you were to graph this, what does a represent in the function f of x equals a times b to the power of x? What is a?
Initial value.
Your initial value. So let's just draw a little quick graph. And where, if the initial value is -3, that's x, that's y, or you could say y equals f of x. Where is -3 located? Down 3 units. So go down 3, draw a point. Now this, then the 1/3 is what you do to the number each time. Now, what am I doing? Am I adding, subtracting, dividing? 1/3. What am I doing? You're multiplying. So if I multiply by 1/3, when I go over 1 unit here, what is -3 times 1/3? So again, -3 times 1/3.
Oh, -1.
-1. It'd be right there. And then I would take 1/3 of -1. What's 1/3 of -1?
-0.333.
Yeah, and so you see that this graph would come in and it would form like this. Now, whoops, sorry, a little too steep there. It would kind of curve like that. Now, what will we call that? Exponential growth or exponential decay? What is always happening there?
It's going up.
It's always increasing. So we'd call this
Growth.
exponential growth. And if you remember, here's the reasoning. Since,
Oh, it's your ratio is greater than.
because it takes both of these. Because A, it comes down to, is it a positive A or a negative A?
It's a negative.
Since a equals -3 is less than 0, that's the symbol for negative. Since a equals -1, -3 is less than 0, and what's the other thing that matters? Our base is in between.
0 and 1.
That's right. And 0 is less than our base, which equaled 1/3, which is less than 1. That's what made this exponential growth. Now, I don't want you to feel like you have to memorize that chart that we had, because we showed all 4 options, a being greater than 0, a being less than 0, b being between 0 and 1, b being greater than 1. I showed you all 4 scenarios, but if you just graph it like that, you can figure it out real quick. Okay, what about the next one? Let's look at number 2 here. Where's my initial value going to be? 8. So 1, 2, 3, 4, 5, 6, 7, 8. Let me get way up there. All right, so I plot this point at 8. And then I multiply by 5/2, which that's the same thing as multiplying by 2.5. What's 8 times 2.5?
8 times 2.5?
Yeah, 20. It's going to go way up there. So this graph is going to come in and look like this. What is that? You'd say it's exponential growth. Now, what's your reasoning when it asks for to explain why?
A is greater.
That's right. Since a is greater than 0, since a equals 8, which is greater than 0, and b is greater than 1. It's exponential growth. Let's do this one more time. All right, this time. It says a is 2. What's that telling us? The y-intercept. Where our y-intercept is at 2 there. So there's the y-intercept. So I'm going to use different colors so these don't all blend together. There you go. Is at 2, and now my b is at 3/4. So where will my next point be? That's like 0.75. What's 2 times 0.75? It's close. It's not 1.75. It's 1.5. So if I went over 1 unit, I'd be at 1.5 right there. So what does it look like is happening to this graph? This is exponential decay. Now, it shouldn't actually come even with the x-axis. It's always decreasing, which means it's exponential decay. But if it asks for reasoning, your reasoning is what? You just have to state is it above or below? Since we're starting above the y-axis, and are we increasing from there or decreasing from there? And b is decreasing. Why is it decreasing? All right. It's in between 0 and 1. That's what makes that happen. So that's a way of just, without having to memorize, how you can figure that on your own, is plot the initial point, multiply it by your base, and see where that next point would be, and you can determine if it's growth or decay. That was lesson 2-3.
I think so.
Give us today. Yeah. Questions on this? All right, moving on. Now we get to hit what I kind of was doing on the geometric problem of lesson 2-4 was manipulating exponential functions. Again, if you're not quite finished and you don't want to panic too much, I will post this to Google Classroom. Okay. All right. lesson 2.4, we learned about exponential functions and specifically laws of exponents. So let's go through these. There were 3 laws plus 2 other rules I showed you that day, which we can write out in a moment. Actually, you want to write those out first? Would that be helpful? First, we had a product rule. I'll give you all 5 right here. We had a product. I say law. I think it's actually property. I don't know. I need one of y'all who are taking Mr. Teresi or Mr. Samron with why do they call some laws? Why do they call some properties? I forget. I need one of y'all to explain it to me. The product property is this: that if you have any base, let's just say the base is 2, and it's 2 cubed times, let's say 2 to the x. How could you simplify that? That's right. That's the product property. Same base being multiplied, you can add the other exponents. One that was similar was the quotient property.
This was a manipulation of exponentials.
Yeah, lesson 2.4. Well, what does quotient mean? Whoops, forgot a T. What does quotient mean?
2 times 3.
2 times 4. Quotient means there's division going on. So let's write it this way. What if we had 2 to the power of 3 divided by 2 to the power of x? How could I rewrite that?
3 minus 2 times to the power of 3 minus x.
Okay, and that I think is similar to the problem I gave you earlier. We did the quotient property. I didn't write down the name, but that's what it was. Would that be helpful to have in your notes? We go back and write that in. That's the quotient property. Okay, I had another one that was called the power property. And what does the power property looks like? It's a power raised to another power. So let's say it's 2 cubed raised to the power of x. And mathematically, if you're like, why does this make sense? Why would this be as it is? Well, first, let me give you the answer. It's what do you do with those two? You multiply them.
3 times the first 3x.
Now, the reason you do that is, let's pretend x is 2 for a second. If it were 2 cubed squared, what that would mean is you have 2 cubed times 2 cubed. And according to the product property, what can you do if you have the same base with different powers? You add them. What's 3 plus 3? 2 to the 6, which is the same thing as 3 times 2. That's why it works. So this is I did this right here would be the product property. Product property. And I proved these are true using each other's properties there. That would be the power property. But I'm just showing you why this works. Okay, those were your actual properties. Then I gave you some other rules of exponents. Do you remember what you could do if you have a negative exponent?
Oh, you can do the reciprocal of that?
That's right. So if we had 2 to the power of negative x, that's the same thing as you take the reciprocal of your base. What's the reciprocal of 2? 1 over 2 to the power of, now you do a positive x. Or you could rewrite that if you wanted to. If it's 1, you could literally put the x down on the 2. Like that. 1 over 2x. Now, I would not do that if that was like 3/4. If that were 3/4 in parentheses, then I would write it as 4/3. And I would leave it in parentheses. But the reason here is because 1 to the power of x. What's 1 to any power? 1. No matter, even if that power is a 0, still 1. And finally, the last rule we had was a fraction exponent.
I think if you were to cancel out a fraction exponent, you just have the reciprocal of that fraction, right?
Yes, you can cancel using the reciprocal. What does this mean? If you have 2 to the 3/4, what that is a dividing exponent. Let me slide this down so you can see better. A dividing exponent is the same thing as a root. This would be the 4th root of 2 cubed, like that. Now with that knowledge. Let's attempt these 3 problems. So I got 3 problems here. I'm going to work through those. All right. I have a slide for each one. So I have them here. So if you want to just take a quick picture so you can see what we're going to do. And now I want to break it down though so I have more space. Number 1. 4 to the power, 4 times 1/5 to the power of x minus 2. Do you see any properties we could use here? Quotient property. What does quotient property mean? So I'm going to rewrite this as a power of 1/5. Like that. Let's do this here. 4 times 1/5 to the power of x. What's it mean to have a subtraction though? You said this is a quotient property, so I can divide this by 1/5 to the power of 2. Very good. That is the quotient property right there. That was the quotient property. Now we could simplify this, and because of commutative property, meaning the order does not matter when you divide, I can rewrite this. First, what is 1/5 squared? Think of what's 1/5 times 1/5. Very good.
Yeah.
1 over 25. Oh, I didn't mean to write a 4th there. My bad. Quality control. Thank you for correcting me. Can I simplify this? If you're going to use your calculator, I would do 4 divided by, and I would do a parenthesis, 1 over 25. But I'm just going to walk through the normal algebra. What do you do when you have, this is all this being divided by 1/25? It's like a fraction being divided by a fraction. You take the reciprocal and you multiply. This is the same thing as, I'm going to rewrite it. You take the reciprocal and multiply it. So I'm going to multiply 25 over 1 times 4 to the 1/5 power of x. What I do is I took the reciprocal of the denominator, which makes this, what's 25 times 4? 100. This is the same thing as 100, and then divided by 1. I'm sorry. That's 100 divided by 1. What's 100 divided by 1? 100. 100 times 1/5 to the power of x. That would be, they say to write it as f of x, so I'm going to write it as f of x. That's our equation right there. Let's make sure we're accurate.
You mean g of x?
It starts as g of x. It says here, write a function f of x, where I skipped over the rules, where f of x equals a times b to the power of x. So a is 100, b is 1/5. Notice a is 100, b is 1/5. That's what I did there. And it's equal to g of x. So that's our function. Let's make sure that these are equal. How can we make sure they're equal? We can plug in a random number. You could graph them, make sure their graphs match. I'll do that way. Let's check the graphs. I'm going to just go to add graph. It's 4 times 1/5 to the power of x minus 2. Gmod. And then we just had 100 times 1/5 to the power of x. What can you tell me about those two graphs?
It's not.
What can you tell me about those two graphs? They match up, don't they? See how they're the same? So we did our math correctly. Okay, let's go 2 more. of the same, using those rules that we have? Mohammed. Let's try this one. What property do you see at play this time around?
Yeah.
Okay, so it's not product property. Product property, right? Product property would look like exponents adding or two bases multiplying. This is not two exponents adding. This is two exponents multiplying. So product property. What can I do with product property? I could separate these out and say that's 3 squared raised to the power of x. That is the power property, like you stated. Y'all are right on this one. Well, how can I simplify that? That's just 5 times 9 to the power of x. And is that in the right form? Perfect. F of x equals 5 times 9 to the power of x. And again, if you want to make it specific, what is a now?
5.
So a remained unchanged. B became 9. You might remember it this way. I said it that a horizontal, talking transformations here, a horizontal dilation, that's when you multiply or divide. A horizontal dilation is a change of base. Horizontal dilation is the same thing as a change of base. Whereas a horizontal translation, number one, a horizontal translation is the same thing as changing a vertical dilation. A horizontal translation becomes a vertical dilation. That was how we said it on lesson 2.4, if you remember. I have one more here. This one I try to get a little bit more creative. Are you good to move on? All right, this time. I got a lot of work. What stands out? This is going to be 2 transformations. Very good.
There's a negative.
There's a negative in front of the x. What I would do is I would GCF that first. Make sure we don't make any silly mistakes. So this is going to be a horizontal reflection. So if you're like, what's that do? Well, we're about to find out. 4 times, I'm going to leave it as 1/2. I'm going to rewrite it vertical style though. And I'm going to GCF out the negative. So if I GCF that out the negative, that's +1. Good. Okay, breaking it down one transformation at a time. What could I do with this horizontal reflection? Think through your exponent rules. That is one of the 5 rules. Not an inverse, that's a good thought, but what do I do with a negative exponent?
You power it.
Technically, this is a horizontal dilation because you are multiplying by -1. So it's going to change the base somehow. What does a negative exponent do to the base?
It makes it flip.
Anthony's got it. Javier's got it. You flip your base. You take the reciprocal. So this is the same thing as 4 times, what's the reciprocal? 2/1. Do I have to actually write it as 2/1? Okay, so I'm going to take away the parentheses just to make it simpler and say it's 2 to the power of. All right, now are we done yet? That was right here. Let me go ahead and write that in purple. That was a negative exponent. Negative exponent. Now you might see why I GCF'd out the negative. Because now it's at x + 1 and we got it correct. Otherwise we would make a mistake there. Okay, what'd you ask? No, the 2 would not be negative. What a negative power does is it takes the reciprocal of the base. It doesn't actually do a negative with the x at all. With the base at all, if I said that right, incorrectly. Okay, now there's one more power at play. Power property at play. The product property, good. This is the product property. What can you do when you have a power property? Let me write first, then talk. Product property. What can you do when you have a power that's adding?
You could do 4 times 2 to the power of x and then times 2 to the power of 1.
Very good. You said it correctly. You could write out the same base multiplying by, whoops, not 4 to the power of x, sorry. 2 to the power of x times 2 to the power of 1. Now I can simplify that.
Simplify it to
And we can get our correct answer here.
8.
Good. 4 can multiply with 2 to the first. What is 2 to the first?
About 2.
That's right. So I'll go ahead and write that out. 4 times 2 is 8 times 2 to the power of
X.
x. Okay, and so what's my a value now? My initial value, 8. Did that change? That's because we had a horizontal translation. Horizontal translation will become a vertical dilation, so it changed from a 4 to an 8. What about my base? It's a 2. Did that change?
Yeah.
And that's because a reflection is you could fall it under the category of a horizontal dilation because you're multiplying by -1, and so it changed the base. So know your exponent rules. We went on from there, and whoops, looks like I have a break here, a little review break. Let's mix it up. Given this function, we're going to do 4 things. We're first going to determine if it's a inverse, if it has an inverse. So inverse was less than 2/8.
In switch x and y.
We'll find approximate, we'll approximate the zeros. That is from unit 1. Determine the equations of asymptotes. That is also specifically, that was, I think, lesson with rational functions. That was 1:819, maybe 1:10 in there. And number 4, use limits to describe the end behavior of any discontinuities. Okay, what'd you ask, Javier? Okay, first, how can we determine if the inverse exists?
Oh, you just switching. Oh, you can just grab it.
Yeah. All right, hey, I want everybody's mind to, you might need to break for a second. Let me just give you, how about this? Let me just pause for a second, let's break. All right, the first thing, here's what we just took a break, now we're back, so phone's up. How can we determine if a inverse exists? I told you a specific way, and this is the reasoning that AP is going to be looking for. How can you determine if an inverse will exist? Okay. And what will you look at when you take a graph?
So basically we'll consider split version.
The values are repeating. X values.
Okay, if you had a table, you could look at something to do with the x and the y's that they repeat, but they're specifically.
Oh, if they
That's how you'll find the inverse
they
is you
pass
change the x and y.
they
it's
pass the
the-
test.
If it passed the test for the inverse, what is the test that we put under?
Horizontal.
The horizontal. That's what you need to remember. That's the reasoning. On the AP curriculum, there's a spot on there, and it talks about the students will understand or can be able to determine if an inverse exists using the horizontal line test. That's what you have to see. Okay, so let's graph this and see if it passes or fails. So let's go graph this equation. Please graph with me. Going to a new document, not saving, just going to clear everything out. We have x to the 4th power plus x cubed. Oh, I need to do a big division line. If you're like me and you started too quick, you can hold down the shift button. Well, that's not working. Okay. You want to highlight the whole thing? You could hold down the shift with one hand, go left or right to highlight. I'm going to hit control divide, so it gives me a fraction. Okay, back up to the numerator. Minus 2x plus 5. And x minus 1. Here's your equation. X to the 4th plus x cubed minus 2x plus 5.
Oh no, I just like acted out.
Go ahead and try again. Question for you. Hey, I want you to be smart here. This is not the whole graph. You know how I know really quickly? This is where I say I want you to be smart here. What you should do is think in terms of the leading term. The leading term should tell you what the graph should look like. We talked about leading term in unit 1. The leading term here is whatever x to the fourth, that's the leading term in the numerator, divided by the leading term in the denominator is. What's x to the fourth divided by x? What's x to the fourth divided by x to the first? We just did exponential rules. X to the third. This should look like x cubed. What does x cubed look like? An S. Are you seeing an S right now?
No.
At most, we're seeing is a parabola, so this is not the whole graph, is it? We need to see more. I'm going to do a zoom fit. Go menu. What zoom fit does? Menu, window/zoom, and choose fit. What fit does is you can tell looking at the arrows, it doesn't change your x's at all. Your x's will stay the same, but it'll change your y values so that you get to see the majority of the graph within those x values. So hit zoom fit.
Can I see your graph? I think I missed it.
I didn't fit.
There it is. So what it does is it tries to show your range. It changes. Zoom fit changes your range. It doesn't change the domain. So the domain stayed the same, -10 to 10. But notice my range changed up from a low value of negative almost 1,025 to a high value of 1,425. You'll see that now. Does the graph look like an S? Or
Well, it does.
there's something that makes it not look like an S. What do we call that break like that when it goes down?
A hole.
That's a vertical asymptote, also known as a infinite discontinuity. Have we used that word in this class?
Yeah.
Can't remember what I've used with AP and what I've used with radar. So that would be a vertical asymptote. But you can see how on the going left to right, how it kind of looks like a S-curve. That's why we just got a discontinuity in there. Okay, so that's our graph. Here's a question for you. Does this graph pass the horizontal line test?
No.
Great. All right, let me go take this over to our notes. All right, so just do a quick sketch in your notes. Make sure you remember why this is or is not, or does have or does not have an inverse. That's a function. Okay. The inverse of f is not a function since y. Since what? What did not pass the horizontal line test? The inverse or f itself? Since f failed and I'm not just going to write HLT, I'm going to write it out. The horizontal line test. The inverse of f is not a function since f failed the horizontal line test. So its inverse would just be a relation, not a function. Make sense on number 1? How we do that? You need to remember horizontal line test. How do we find, number 2 said approximate zeros. How do you find zeros with the calculator? Do you remember?
Intercepts.
They are the intercepts. Now I'm going to make my graph be a little bit easier to see. Now that I know what the graph looks like, do I need to go this low? No, I'm going to change it to like -200 and +200. Let me see if I'm able to determine how many zeros this has better. All right. How many zeros does this graph have? No zeros. I'll use full language. The function f has no zeros. What that means is the numerator, you could not solve this equal to 0. It would not work out. Function f has no zeros. Remember, zeros come from the numerator. Okay, what about this? Hey, Chris, come on now. Number 3, determine the equations of any asymptotes. So first and foremost, this does have a very obvious vertical asymptote. Vertical asymptotes occur when you break a rule of the domain. And if that value cannot be canceled out with the numerator, which would make it removable, but we don't have to worry about that because we already know it doesn't have any zeros, so it cannot cancel out. What can you not divide by?
0,
0. So what value of x would not work for this domain?
1.
1. Notice if you put this on your graph, this would be a vertical asymptote at x equals 1. Let me get that right on the line there. That's a vertical asymptote at x equals 1. There is a vertical asymptote at x equals 1. Is that the only asymptote?
Yeah.
Ah, good thought, but no. This right here is what I tell you it's going to be shaped like. An S curve. That leading term is another asymptote. So there is a vertical asymptote. There is also what's going to be called an oblique asymptote. Now, how do we find the oblique asymptote? So here I'm going to say oblique asymptote. And this is a review again from rational functions. This was lessons 1.8, 1.9, and 1.10 that we did this. What you do is you simply put divide. Now, what's the easiest way to divide? You actually do the math. This says to divide. What's the easiest way to divide that I taught you? Easiest technique. That would be to multiply. Would be box.
What's it called?
Yeah, it's a type of division. Starts with an S.
Synthetic.
Synthetic. Let's use synthetic. You start with what does x equal? Step 1.
So
What does x actually equal? What are you dividing by?
that's supposed to be 1.
Positive 1. Okay, draw your line this way. Step 2 is you write out your coefficients.
So
1.
1x to the 4th,
1 to the 3rd.
1 to the 3rd.
0.
Good that you remembered 0 because I don't have any x squareds.
-2.
-2 and
Other 5.
plus 5. You leave a gap. Step 3. Follow your
No.
mama. What did that mean?
1.
Okay. So we drop the 1 and we multiply first. 1 times 1 is 1. What's 1 plus 1?
2.
That's a positive, so I put that. So that's a positive. Okay, what's 2 times 1? 0 plus 2.
2.
Multiply again. 2 times 1? 0. And 0 times 1 is 0. And we end up with positive 5 as our remainder. Now, that means it's not a factor. Remember that? And so this is the oblique asymptote right there. It started off as x to the 4th. So when you drop it, it becomes,
X to the 3rd.
so the equation would be 1x to the 3rd. By the way, if this was a fraction, you'd have a step 4 where you divide by the denominator again. The quotient, you take your quotient and you divide by the denominator again. But it's 1x to the 3rd plus 2x. Do I need to put plus 0? No, that's your oblique asymptote. So we had x equals 1 and y equals all this. So let me go back to the calculator one more time. This is pretty cool.
Where'd you get the? Oh, no.
Go to your calculator one more time and press tab for new equation. Actually, I'll do menu. I'm going to do graph entry and I'll type this in as a relation. Yep. So I can type it in as y equals. And I'm going to do a relation 2. I press down just so it's a different color. I just told you the equation is y equals x cubed. What came after x cubed? Was it 2x squared? And was it 2 plus 2x? And that was it, right? Check that out. What do you notice? Do you see on the outside how it lines up? Now, does it have the middle section? Does it still have that discontinuity? No, an asymptote just means the graph as you increase without bound, whether it's x's or y's, that the graphs approach one another. So this graph is approaching it as the x's increase without bound or as they decrease without bound. And here they're not, the x's are not increasing or decreasing without bound. So I'll just add that in there, and I'm going to take that picture and add it back over. And we'll move on from that. So there's our two asymptotes. I don't know, why is that not going to the front? Order, bring to front. There we go. So let me get that back on. And finally, step 4. What if we had to write limits? How many times? Remember, a limit doesn't tell you where the graph is. A limit tells you where it's going. So using this picture here, how many times does the blue graph actually go somewhere? Let me actually not do that one. Let me do this picture. How many different limits do we need here? How many different arrows would this graph have? 4. 1, 2, 3, 4. So we're going to write 4 limits. Okay, this will be limit 1 right here. What's happening? Let's start with the x values. When I'm on this limit here, where is it going? Is x increasing or decreasing? It's decreasing without bounds. So say negative infinity. What's y doing? Is it rising, falling, or is it approaching a constant value? This is falling. It's decreasing without bound as well. So that's our first limit. I'll go clockwise. Let's say this is our second limit here. What's happening to the x? Is it decreasing without bound, increasing without bound, or is it approaching a constant number? It's approaching a constant number. Now, what's the number that on this graph is approaching? I agree. It's approaching 1. And something that's going to matter later. Are we approaching 1 from the right side or the left side? Which side is this graph approaching 1 from? The right side. So you need a plus there. Focus in as best you can. I know it's hard with that going on. Okay, what's happening to the y's? Are we rising, falling, or is it approaching a constant, getting flat, approaching a constant value? No, the y's. What's the y's doing? Rising. What's the symbol for rising? Positive infinity. Okay. We'll do this as limit 3. Limit of f of x as x approaches some value. Okay, what's happening to my x's here? Are they increasing without bound? Are they decreasing without bound? Or are they approaching some constant value x? They're increasing without bound. So that would be positive infinity. What's happening to my y values here? Are they rising, falling, or is it getting flat, approaching some constant value? It's rising. Okay, and last one. Call this limit 4. Put an arrow there. Let's start with the x. Are the x values increasing without bound? Are they decreasing without bound? Or are they approaching a constant x? You're thinking of y's. Don't think of the y's. What are my x's doing? Is it going to the right? Is it going to the left? Or is it getting really flat on one x value? Really flat. What's the x value it's getting flat with? 1. If it's really flat on the x, you have to tell it plus or minus side. Which side are you coming from? The left or the right here? Going from the left. That's a negative. 1 minus. Means they're coming from the left. Now, what happens as we come from the left? Does the graph, as we approach 1, as we are heading to the x value 1, what's happening to the y's? Am I rising, falling, or getting flat? Falling, negative infinity. There would be your limits. There's a review of that stuff, so you don't forget that. All right, I think we've now hit some problems here. That kind of round out the lessons. We started doing a lot of data. We also did some composition and inverse, which I kind of threw in last problem. It says the table gives the number of alternative fuel vehicles in thousands used by the United States for select years from 96 to 2010. The function A is defined there, is used to model the data in thousands from 6 less than or equal to t, which is less than or equal to 20, where t equals 6 corresponds to 1996. So what does t equals 0 represent? T equals 0 would be
1990.
1990. What would t equals 10 be? 2000. Okay, make sure y'all are tracking. Which of the following could plot the residuals of the model? All right, how could we figure this out? What does it mean to have a residual? What is the formula?
Minus.
Very good. Residuals equal to actual minus predicted. What was the difference with error?
The actual value. What is it?
It wasn't the same.
So this was lesson, we did this on 2.5 and 2.6. But 2.5 was going through it all for exponentials. 2.6 was determining if it's linear, quadratic, or exponential.
With the tab. Plotting exponential things.
Yeah, just you can do lessons 2.5 and 2.6. To remind you, the error, all the difference with the error is the absolute value of the residual. So you never take a negative with error. You say, regardless if it's a positive number or a negative number, you just say whatever the value is. Okay, I just want to put those formulas up there. All right, so let's find out what are we supposed to have at, this is year, what year? Which was t equals what number? 6. We're supposed to have this many. That's the actual. Make sure you remember this is actual here. So let's go see what the predicted is. Here's the model. This would be the predicted, okay? So let's go to our table. I'm gonna go new document here, clear it. Let's graph that equation. It was a fraction, so do fraction first, and I've forgotten it's 4615t. 4615t, except my calculator needs to do an x, minus 8727. 4615x minus 8727 over, I'm Quentin, make sure y'all are following along here, negative 0.542t squared. So I'm going to say x squared plus 15t plus 15x plus 1. Whoops. Plus 1. Let me graph that. Now, I don't care to look at the graph. What do I care to look at? The table. And the first value I want to compare is 6. So what's the predicted at 6? 265.261. All right, let's do this. On over here, what I'm going to do is I'm going to add a little column, and I'll call it predicted. What did y'all have for your predicted value? 261. Okay, so if we took actual minus predicted, what should we get?
0.261.
Positive or negative? Negative. Okay, so here's 6. Could that be negative 0.261, you think?
Oh yeah.
What about here? No, it's positive. What about here? What about here?
No.
So we already got our answer. let's just check it though. Let's do one more just to make sure. Let's go to year 8. This is t equals 8. Which for our calculator, we need to go to 8 right there. $326.64. $326.640, I think.
Yeah.
641 when you round it. Whoops. 641. So actual minus predicted is like negative 31, basically negative 31.641. All right, does that look like it's negative 31? Maybe.
Very something.
All right, looks good. Let me throw these in here. There was our first value that we looked at. Oh, there's our second, sorry. That was our second value. And well, I'm just gonna leave it like that. This is where I got both of these values here and there that we checked out with. So do y'all have any questions on how to do a residual? Do y'all remember? I did not. Let's do this. The time we have left, let's make sure we remember how to do a regression. Let's say here's our table. Let's just type in the first 4 values. And this time let's come up with a exponential growth model. Okay, so let's just do the first 4. We're going to do an exponential growth model. I'm going to change my calculator so we can see both. Would we add in the whole year? No, absolutely not.
Okay.
So I'm going to ask a few questions as we go here. So new document here. Let's enter in our data. Where do I enter into the data? Okay, now we need to put variables. So I'll put a T this time. And this is the number of vehicles. So I'll just put V for vehicles. So what do I put for the first year? 6, 8. What about 10,000? 2,000. And then what I put O2? 12. Very good. Time is 12 in 2002. Okay, and we'll put in the values 265, 295, 394.7, and 471.1. Now, remember, you have to put in variables and you have to leave the box. You can't have the cursor. Like if you're still with the cursor, you can't do a regression. So make sure you leave the box so you have no cursor showing and you have variables in there. What type of expression did I just ask you to find? Let's do exponential growth. So how do I do that? You press menu, statistics, stat calculations, exponential. That's what I want. I want you to do an exponential regression. What did I title my X list? T, and my Y list? V. Again, pay attention to where it saves it. I cleared my calculator. You might not have. I got an R squared of 0.97. What do you think? Good or bad? That's good. That's a good model. All right, here's a different question though. How could I see this like a plot?
Oh, add page,
I'm going to add a page, control doc,
data statistics.
data and statistics. All right, great. Now, if I wanted to see the regression as a whole, like its own scatter plot, you would put, what is our original X value? T, and what is my original Y? V. And this could show me what it looks like. So you can see why I'll do analyze here. I'm going to add in the equation. If you do analyze, you can do regression again, and I'll show exponential. And you can see why it works pretty good. You see how that goes between those points, all right? Okay, but if you wanted a residual, that's different. This is not the residual plot. that you would, I'm gonna add another page, you would still go to data statistics, and I would still leave the X value. The X value never changes, but now I change my Y value. Which one do you think I would choose? Stat dot residuals. And that shows you the residuals. And so our first point on our equation, this would be, if you had a value of 8, let's just pretend this is 8. I know it's 8.41 or 8.42. I'll just say 8.42. If you had a residual of 8.42, what is that practically telling you?
That's the amount of error.
8.42 would be the error, but it's telling you something else.
Like how far overshot?
Oh,
Would
it
this be an
overestimated.
underestimate or an overestimate if you had 8.42? Wrong. That means the actual is higher. So up above is your actual. If your actual is higher than the predicted, we underestimated. This underestimated, this one here, overestimated. This one, underestimated. This one, underestimated. It's backwards when you look at it because it's actual minus the predicted. So if it's above, it underestimated. If it's below, it overestimated. Okay, just want to make sure you know that this one underestimated by 8.42. This one overestimated by almost 19. So if I ask you what's the error on this point, one more time before I move on. If I ask you what's the error on this point, what's the answer?
18.9.
18.9. Why not negative 18.9?
Because
The error doesn't care about if it's positive or negative, just wants to know how much was it wrong by. Questions over that? I think that's a wrap.